Now we will consider how to apply Gauss law to find the electric field of an infinite plane of charge. Of course, non-conducting plane in this case. So here the charge is distributed over a plane of charge, and this plane extends to infinity in all directions. I've just shown here that it's true. So it's extending in all to infinity in all directions. Okay, and this charge is uniformly distributed over the area, and the charge density is sigma in this case. It has a uniform charge density, and this charge density is sigma. Again, I will apply Gauss law in order to find the electric field here. Now, before applying Gauss law, I have to before starting my calculations, I have to apply my strategy. I want to find a Gaussian. Of course, what requested is to find the electric field at a distance, some distance above, or at points above the infinite sheet, or below it, if in this situation to the right or to the left. Okay, there is a full symmetry, by the way. In this case, the electric field at points here is the same as the electric field at the point here, because this is a sheet of charge. Okay, so what you see, the environment that you see from this side is exactly the same as the environment you see from this side. Okay, so the electric field in this region is exactly the same as the electric field in the region which is a mirror image of it across the plane. So this is important. So okay, I'm at some distance here above the sheet, and I want to find the electric field. I need to choose a Gaussian surface that will somehow pass through this point, the first thing. And the second thing is, I needed to have E uniform on the surface or on part of it, and E parallel to dA on the surface or on part of it. So let me start by saying, what does the symmetry tell me about the electric field in this region due to this infinite plane of charge? Now, the first thing is that it's best to think of it, that the ground, this infinite plane of charge, is the floor. So the whole floor is covered from the charge, is covered with charge, and it's extending to infinity. Now, evidently, if you are at some distance, a given distance from this floor, and you move around, keeping your distance at least, then definitely you will see the same charge environment. You will see the same charge environment. And so the magnitude of the electric field when you move around, okay, keeping your distance, should be the same. So this is the first thing that I know. So the magnitude is the same because you see the same charge environment as you wander about. So the electric field doesn't change in this direction. It might change. We will see it is not. It will not in this case, but it might change when you go far, maybe. But as far as you keep your distance from the plane and move around, because you see the same charge environment, the electric field will not change. This is something, the first thing that the symmetry tells you. The second thing, this is infinite in all directions. And so each point here is above a middle point, because when it's infinite, any point on the floor is a middle point, because it's extending to infinity in all directions. And therefore, the electric field here will be only normal, because the same argument that we have introduced in the case of the line, all the components of the electric field that are not normal will cancel each other due to the symmetry. And the electric field will be only upwards, or in my case, or perpendicular to the plane of the sheet. This is the thing that I know. Therefore, so at some distance from the field, this is how the electric field lines will look like. Now, knowing this, we choose the correct Gaussian surface. As I mentioned, choosing the right Gaussian surface takes experience. And now, why we are saying it in a a couple of minutes, those who did it first actually have put in a lot of thinking, doubtlessly. So we can choose our Gaussian surface in this case as a cylinder of small cylinder or large cylinder, doesn't make difference, and we make it penetrate through the charge distribution. Okay? Now, what I know about the electric field on this cylinder is the following. On the curved part, the electric field lines, because the electric field is normal to the cylinder, on the curved part, the electric field is parallel to the surface. In other words, it's normal to dAs here. So there is no, it doesn't contribute to the flux. On this and this side, which is the other side, the electric field is definitely the same, and it is perpendicular to the Gaussian surface. Okay? So this is the Gaussian surface that I choose based on the symmetry of the electric field that I have, that follows from the symmetry of the infinite uniformly charged plane of charge, and now I can proceed and do the calculations. Having discussed the symmetries of the electric field and the Gaussian surface, we move now to do our calculations. Now, this is a side view of the charge distribution, okay, of the plane, and this is the charge, and this is the Gaussian surface that I have introduced, and I want now to apply Gauss law to find that Gaussian surface. Now, as we have just noted, the electric field here should be in this direction. The electric field here by symmetry, because we have symmetry on both sides of the infinite plane, is in this direction. The field along this cylindrical surface is parallel to that surface. Okay? Now, evidently, dA also in this direction is here. dA here is here. It's normal to the surface. Now, on this cylindrical part of the surface, the dAs here are always normal to the cylindrical part. Wherever you go, it's always normal to the cylindrical part, and since the electric field lines are tangent to the symmetrical part, then the angle between the electric field, the direction of the electric field at the cylindrical part of the surface and dA is always pi over 2. Okay? Now I apply Gauss law to this surface and see how can I find the electric field. Well, Gauss law, it is just E dot dA equals Q enclosed divided by epsilon naught. The integral is over the whole closed Gaussian surface. And in this case also, what I do is I note that this surface, closed surface, is composed of 3 portions. Let me call this, for example, A1, call this A2, and call this A3. These are the 3 surfaces. And therefore, the integral over the closed surface can be decomposed into 3 integrals. Each of them is over one of these open surfaces. So this is equal E dot dA. I should not put a circle now because it's not closed. So A1 dot A plus integral over A2 E dot dA plus integral over A3 E dot dA. Now I start with E3, the A3. Now this is equal E dA cosine pi over 2 all the way, because as I have just mentioned, dA and the component of the electric field at this surface are always perpendicular to each other, and this quantity is what? This is 0, so this reduces to the integral of the electric field over these 2 open surfaces. In other words, the flux through these two surfaces. Now, again, E and dA are parallel here, and from our arguments at the beginning when we first discussed the problem, the electric field is uniform here, so this reduces immediately to E dot dA A1 plus E integral over dA A2. Okay? Now, I write here that A1 is equal, A2 is equal A. So the area of E1, of A1, this surface and this surface, they have the same area, and so just call it A. So this quantity becomes twice EA. So this is the left-hand side of the integral. Now, what about the right-hand side? This is equal Q enclosed divided by epsilon naught. Now, what is Q enclosed in this case? I need to write down Q enclosed, then divide by 2A, and then I will find my electric field. What is the Q enclosed? Q enclosed, by definition, is the area, is the charge enclosed by the by the Gaussian surface. So, what charge does this enclose? You know, this Gaussian surface cuts the plane. When it cuts the plane, it cuts a circle which has area equal to A1 and A2 or A. Okay? So the only charge enclosed with it is the charge on this circle. And the charge on this circle is equal to the charge density sigma multiplied by A. Therefore, so from here, Q enclosed is equal sigma A over epsilon naught, and therefore you can, this A cancels, and you get E is equal sigma over 2 epsilon naught. And this is the electric field of an infinitely charged plane, okay? Non-conducting plane. Non-conducting plane, it's important, because for a conducting plane, things are a bit different. Now, this is an interesting result. The electric field is independent of how far you are from the plane. Okay? So whether you are here or here or here or here, the electric field doesn't change. It depends only on the charge density. The more the plane is densely charged, the higher is the electric field. So the higher the charge density, the higher is the electric field. This is the only factor. And we have a uniform electric field in this case because it doesn't change, it's constant, and we have seen that it's always pointing away from normal to the plane and away from it. Therefore, if you want to plot the electric field of such a plane that extends to infinity, then the electric field lines, then these are the electric field lines. They extend all the way. And the same applies here. So one way of generating an uniform electric field is to have an infinite plane, a non-conducting plane of charge. In this case, on both sides of the plane, you will have a uniform electric field directed for positive charge, directed away from the plane and perpendicular to it. For a negative charge, the electric field lines, the only thing that will be different is that the electric field lines will be directed towards the charge, okay? Towards the plane, I'm sorry. So it will be, again, uniform, equally distanced, but they are directed, they will be directed towards the charge. So this is the uniform, this is the electric field of an infinite non-conducting plane of charge.